welcome you all. Today I am going to deliver lecture 5 of module 6, which is on the treatment and disposal of sludge. So if we recall our previous lectures, we have started with the sludge characteristics, various equations to be used to determine the quantity and volume of the sludge, and then we have seen the design of gravity thickener, then sludge digestion process, and now we are going to learn about the sludge drying bed, its design, and various types of sludge drying bed like unplanted and planted sludge drying beds. And then we have also covered here the design criteria which are used for design of sludge drying bed, along with the various steps to be followed in design of sludge drying bed. And then finally we have taken few numericals which will illustrate the design procedure and the various design parameters to work out for assessing the performance of sludge drying bed. So here if we see what is basically this sludge drying bed. So this is one of the simplest and oldest techniques which are used for dewatering of the sludge. And if we see, that is composed of impermeable beds overlying with the different layers of filter media made of gravel and sand, above which the sludge is applied, and below this the under drainage systems are provided, perforated pipes are provided which will collect the entire filtered water from the sludge and will take out of the sludge drying bed and will be recycled back to the primary settling tank for its complete treatment process. Whereas the sludge which are dried, which remains on the top of the bed, gets dried in due course of time through the evaporation and open sun drying, and then finally it is collected as a sludge cakes by excavating the topmost layer of the sludge drying bed. So if we see during rainy season, the operation of this sludge drying bed becomes difficult because of very slow rate of evaporation. So if we see out of 12 months, we can operate this sludge drying bed normally for 10 months only, considering 2 months rainy season period for which these sludge drying beds are discontinued from its operation. So this is a kind of facility which are mostly used for dewatering of the sludge. Before we go in more details, let's see have a picture where if we see these are the number of beds, rectangular beds, they are provided on both sides here and there. So these sludge drying beds, they are mostly rectangular shape. So if we can see here, these are the number of rectangular plots, and this if we see, that is the longitudinal pipe which consists of number of transverse pipes. So these are the sludge inlet through which the sludge enters into these different beds, enters into first this longitudinal sludge inlet pipes. From here these are the outlets through for different sludge drying beds. So like this the entire sludge is applied onto the different beds, and then it is allowed to filter the water and then let the top bed of the sludge, which gets deposited on the top layer of sand, gets dried, and then finally it's excavated and taken out of the sludge drying bed so as a fresh layer of the sludge can further be applied. And in this there are the under drainage systems which are provided, which will collect the filtered water and will take out of the sludge drying bed and will be recycled back again to the for complete treatment system to the sedimentation tank, wherein this will be further treated to the in the treatment plant. So this basically says the plan, and this is the cross sectional view of the sludge drying bed. If we can see, this is the longitudinal pipe which are made here, and these are the transverse pipes through which the sludge enters and get spread over these rectangular plots here and there. So both sides we can see number of beds of particular size they are made of. And here if we see the cross section, so we can see this is like the sludge inlet pipes, these are the transverse pipes, and this is basically the sludge layer. Below this there is the layer of sand basically that is provided around 20 to 30 centimeter, below which there is a gravel layer provided to support this layer of sand and the sludge layer. And at the bottom there is a under drainage system which is provided to collect the whatever the filtered water through the entire cross sectional area, that will be collected at the bottom here, and through this pipe it will go out of the sludge drying bed. So this is basically the complete diagram to understand the structure of the sludge drying bed. And if we see, they are basically the types of sludge drying beds. So basically they are two types, like one is unplanted and another one is planted. So unplanted type of sludge drying bed does not have any plantation over the sludge drying bed, whereas in planted type of this sludge drying bed that are designed like red bed system, where this unplanted one that is designed as the sand filters. So let's see one by one the layout and the design of both types of sludge drying bed. So this is basically the cross section of the unplanted type of sludge drying bed. So here if we can see this top layer, that 15 to 13 centimeter, that is the layer of the sludge we apply. Below this if we see, that is 20 centimeter depth layer of sand, and below this everywhere here there are the gravel media that is provided, and this is basically the 100 to 150 centimeter diameter pipes. They are basically open jointed earthen pipes which will collect the entire filtered water from this sludge bed, and that will be collected through this open jointed pipe and will be taken out of the sludge drying bed for dewatering. So this is basically conventional type of sludge drying bed which are mostly used in for disposal and dewatering of the sludge. So here if we see the design of this type of sludge drying bed, that is basically designed as like the gravity filters we design, like slow sand filter, rapid sand filter for the water treatment process. And this type of basically the drying bed that requires frequent desludging after one cycle is completed. So this desludging has to be done, and again the bed has to be prepared for the next layer to be applied on the sludge drying bed for dewatering. So these are the basically the limitations of this unplanted type of sludge drying bed. But if we see in planted type of sludge drying bed, so here we do not require any kind of desludging after every cycle, and this design concept that is based on the design of reed beds or constructed wetland system. And here basically the kind of porosity which is required for filtration of water, that is maintained in this system through the root system of the plants which are grown on the top of the bed. So here the design if we see, that is the basically the topmost layer, that is the layer of the sludge we apply. Below this is like the sand bed, and below this is like the gravel media, and here all the water which is filtered over this through entire cross sectional area that will be collected, and here this is the basically outlet through which the entire water will be taken out and will be recycled back to the treatment plant for further treatment process. And one more difference here, before the sludge is applied, there is a screen is made here. So this entire sludge that has to be passed through the screen. So whatever the debris, sludge debris and some bigger size of impurities which are present in the sludge, that is basically removed here, and then it facilitate like proper filtering of the water. And at the top, if we see, there are the number of aquatic plants we grow, so that every time we need not to desludge the dried sludge, and then again we can apply the next sludge layer without any desludging operations. And these are basically the two ventilation pipes. They are provided so as if anything like further whatever the gases which are produced during the further decomposition process, they are taken out through these pipes and discharged into the atmosphere through these ventilation pipes. So these are the different types of sludge drying beds we use, but normally in almost conventional system we follow this unplanted system because of lot of trouble in growth of these aquatic plants onto the top of the sludge drying bed, and the difficulty in every time preparing the bed and again applying the next layer of sludge. So because of this, the use of this type of sludge drying beds are mostly limited. So then let's talk about the various design criteria which are used for design of sludge drying beds. So mostly this having two criteria, that is basically the size of the bed and the requirement of the surface area for proper filtration of the water from the sludge, separation of water from the sludge. So here if we see, that is the important criteria, which is the dry solids loading rate, or we also say sludge loading rate. So sludge loading rate, basically that is defined as the amount of dry solids that can be applied per unit area per unit time. So that is the sludge drying bed, and usually this is expressed in terms of kg dry solids per unit area per annum. So this is the unit, and this is basically applied to determine the surface area required for sludge drying bed. And then overall, as a thumb rule, we have to check per capita the sludge bed requirement is 0.1 to 0.25 meter square. So this is another criteria for which we have to check our design parameters, whether our design follows these two important criteria. So this for digested primary sludge, and if we have a mixed sludge like primary and secondary sludge, then the same criteria we follow, like 0.15 to 0.28, which is slightly different from this. And then here, instead of 80 to 120, here we take 60 to 120 kg of dry solids per meter square per year. And then for the size of the bed, if we see that the length we can take from 6 to 30 meter, whereas range of width we take that is around 3 to 8 meter. In normally the size what we prefer, that is 30 meter by 8 meter. So this is the size of the one bed that normally we consider while designing the sludge drying bed as a conventional practice. And this is again the important criteria, that is the depth of the sludge bed, because it directly affects the rate of evaporation. So we try to have minimum depth of the sludge so that the bed gets dried and the moisture gets evaporated. If the bed thickness is more, the rate of evaporation will be less. So we try to maintain that sludge thickness which is applied onto the bed should not be more than 15 centimeter. Normally the range is 15 to 30 centimeter, but we try that while designing it should have minimum prescribed range. And then if we see, that is the sludge drying time. So how much time it takes for sludge to remove its moisture, that is normally 2 to 4 weeks. That also depends upon the type of the sludge, whether it is digested sludge, whether it is undigested primary sludge or it's mixed sludge. So depending upon the type of the sludge, that sludge drying time differs, and usually we, for all design purpose, we take usually 2 to 4 weeks for its drying time. And then this is specific sludge loading rate, which is another criteria, that we can take like 50 to 210 kg per meter square per year. So these are the various design parameters which are used in design of the sludge drying bed. So then let's see what are the various design steps to be followed while designing a sludge drying bed. So we know that the sludge drying bed is designed based on the total amount of dry solids that can be applied per unit area, per unit time, and time basically that the sludge loading rate that is given as per year. So we have to first complete the total amount of that dry solids which are produced per year, and then we can assume the appropriate sludge loading rate for different types of sludge depending upon the type of the sludge. And then using this criteria, if we divide the total amount of the dry sludge produced with this sludge loading rate criteria, so we are able to compute the bed requirement, the surface area requirement of the sludge drying bed. And then this requirement has to be checked per capita basis, like if it should not exceed to the prescribed range. And then what we can do is, like having the total surface area, we can assume the size of the bed, and for one bed we can calculate the area, and then we can find out how many number of a particular size of bed is required as per the total surface area requirement of the bed. So this is the next step. And finally then we have to check that the thickness of the sludge should not exceed by 15 centimeters. So for that we have to assume the number of the cycles that can be performed in a year. So assuming like 2 months rainy season, the sludge drying bed operations are discontinued, and 1 month time will take for one cycle to complete. So total out of 12 months we can have 10 number of cycles. So depending upon the number of the cycles we can operate in a year, we can calculate the depth of the sludge that is applied over the sludge drying bed. And then it has to be checked that it should not exceed by 15 centimeter for better performance of sludge drying bed. And then also we can finally check as per the actual size of the bed how much the surface area is provided, and this must always be higher than the required surface area of the sludge drying bed, which we calculate using the sludge loading rate criteria. So these are the different steps that we can follow to design the sludge drying bed. So let's see, take some example, and then using this example we can illustrate how the design of the sludge drying bed can be carried out. So if we read out this example, so here we see that we have to design a sludge drying bed to dewater the digested sludge which is produced from a wastewater treatment plant, which is based on the activated sludge process. And here following data we need to assume for design of the sludge drying bed. So here if we see that the population data is given, like the treatment plant is serving for a population of 50,000, and then here the another criteria that is given as per capita dry sludge produced, that is 70 gram per capita per day, and the solid concentration in the sludge that is also given as 7%, and this is the specific gravity of the sludge solid, that is 1.02. So here if see what we have been given is like the population and the per capita per day solid contribution. So using these two data we can find out how much total dry solids will be produced in a day, and then using the sludge loading rate criteria we can find out the surface area requirement, and then we have to also consider that the solid concentration, that is 7%. So how this design we will be doing? So that is, you see here the solution is given here. First of all, we have computed the amount of the total solids they are produced per day, and if we can calculate for per day, then in a year also by multiplying 365 we can calculate per year total solids produced from the treatment plant, for which we have to design the sludge drying bed. So here, for estimation of the total amount of dry solids produced, that is as per the numerical, the per capita sludge contribution, that is given as 70 grams of dry solids per capita per day, and we have been given with the population also, that is 50,000. So if we multiply this with the per capita contribution of the dry solids, so we'll get total amount of the dry solids which are produced per day. Since the value is given in grams, so it will come in a total amount of the sludge in gram per day. Since the quantity will be very high, so we have converted this into kg per day. So here 10 raised to the power minus 3, we have to further multiply to convert this gram into kg. So if we estimate, we'll get this total amount of the dry solids which are produced, that is 3500 kg per day. And then once we have calculated amount of the total solids produced per day, then we can find out the surface area which is required for designing the sludge drying bed, because this dry solid loading rate, that is to be assumed here, as this data is not given in this problem. So here we have assumed as per the type of the sludge. If we see, the sludge is basically from activated sludge process, so that the criteria that we can assume, that is 100 kg per meter square per year, which is within the design range for activated sludge process. So accordingly, if we find out the total surface area required for the sludge drying bed, so this will be equal to the total amount of the dry solids which are produced in a year divided by this dry solid loading rate, the assumed criteria for solid loading rate or sludge loading rate. So here if we see 3500 kg per day is generated, and if we multiply with 365, so we will get total amount of the dry solids which are produced in a year, and then divided by sludge loading rate or dry solid loading rate, which is we have assumed 100 kg. So here after putting this 100 kg, we get this total amount of area which is required, that is 12,275 meter square per year. So once we get this total area, so we can check for per capita requirement of this area. So here this is the total area divided by total population for which it is designed. So that comes around 0.255 meter square per capita, which is within the prescribed range as per the design criteria prescribed for sludge drying bed. So we can say our design of sludge drying bed as per the per capita requirement, that is satisfied. So once this check is completed, then we have to find out how many number of beds are required. So for this we have to presume the size of one bed. So let's presume or assume the size of one bed to be 30 meter long and 8 meter wide. So the area for one bed, that will be something 30 into 8 meter square area. So for how many bed will be required for such a size of beds? So we can find out by dividing the area of one bed to the total area required for the sludge drying bed. So this is 12775 meter square, that is the total area required, and then this is the size of one bed, that is 30 meter by 8 meter. So by putting the value here in the equation, we can get the total number of bed that is required, that is something 53.22. So this is not a complete integer, so we have to take the next positive integer value, that is 54 number of beds. While deciding this, we cannot take it like 53, because if we make 53, so total area requirement will not be met. So taken always higher side instead of taking the lower side. So now for this, we have designed like 54 number of beds are required of this size. So now another check, that is like the thickness of the sludge that will be lying on to the top of the sludge drying bed. So that has to be checked. So for that we have to presume like how many number of cycles a bed can be performed in a year. So as I discussed, there are like 2 months rainy seasons. So if we subtract 2 months rainy season, so we have 10 months for operation. And to complete one cycle, like including the application of the sludge, dewatering of the sludge, drying of the sludge, and then again excavation of the sludge. So this complete cycle takes about 1 month. So in a year we presume that total 10 cycles can be performed for every bed. So looking into this consideration, now we can find out how much thickness of the sludge will be there on the top of the bed. So for that we have to first estimate the volume of the digested sludge for this much kg of the dry solids. So this formula we have to look into, that is the Ws divided by rho W into specific gravity of the sludge into percentage of solids. So we all know this data, that is total solids which are generated, that is 3500 kg per day, divided by this the density of the water, which we can take as 1000 kg per meter cube, and then this is the specific gravity of the sludge, which is given already in the problem, that is 1.02, and then this percentage of the solids that are 7%, so we can write as 0.07. So by putting this value, we can find like per day this much amount of the sludge that will be generated, so equal to something around 49 meter cube per day volume of the sludge that will be generated. So from this volume we can further find out the depth of the sludge bed required. So here if we calculate this sludge depth, what will be there for the given size and the given volume of the digested sludge. So here if we can use this formula, like total volume of the sludge applied in a year divided by number of the beds divided by area of each bed, and then number of cycles of each bed that can be put for operation. So by putting this value, we can find out how much will be the depth of the sludge being applied onto the sludge drying bed, so that we can check that it should not exceed by 15 centimeter. So let's put this value here. So total amount of sludge applied per year. So this is basically in terms of volume. So per day this much volume is generated. So if we multiply with this 365, so we get total volume of the sludge which will be generated in a year. So here if we see the number of beds, that is 54 number, and then the area of each bed, that is 30 into 8, so that is 240 meter square area for each bed, and then 10 number of cycles for each bed. If we divide, we get the thickness of the sludge, that will be equal to 0.138 meter, which is less than this 15 centimeter, approximately equal to 15 centimeter. So I think this also confirms the prescribed range of sludge thickness, that is around, should not exceed by 15 centimeter. So here finally we can recommend like total number of sludge bed to be designed, that is 54, but always we have to take plus 2 number of sludge drying bed as a standby bed, so that if any of these beds gets some repair, so these standby beds, they can be used, and the operation of the sludge management is not hampered. And each of these beds will have a size of 13 to 8 meters. So this is the answer for this problem. Then we can check again the total number of beds that has been provided depending upon the actual volume of the sludge. So if we see this 49 meter cube per day is generated, so in a year this much of volume of the sludge will be generated. And if we see the volume of the sludge that each bed will handle with 10 number of cycles of operation in a year, so how much volume a single bed can occupy. So we can see the number of cycles, that is 10, one bed area, that is 13 to 8 meter, and the sludge thickness we can take up to 0.15. So this much meter cube of sludge it can handle a single bed in a year. So the number of beds required as per this calculation comes to total amount of sludge being produced divided by volume to be handled by a single bed. So here if we can see, this value comes around 49.68. So this is 50 beds. So within 50 beds the total requirement is fulfilled, and we are providing in fact 54 beds. So this is well within the acceptable range. So this rest of the bed at the time of emergency can be used as a standby beds. So if we again see the problem, that is another numerical, we have to design the sludge drying bed for the digested sludge which is obtained from a low rate anaerobic digester. So here the sludge which is produced is already digested and treating basically a mixture of primary and activated sludge process. So this is the mixed type of sludge, digested sludge, and this is produced from wastewater treatment plant having activated sludge process of capacity 50,000 meter cube per day. So following data we need to consider while designing the sludge drying bed. So here directly the volume of the digested sludge per day is given instead of giving the per capita contribution of the solids or any other data. So here directly the volume of the sludge is given, and here again if we see dewatering, drying and sludge removal cycle that is given, that is 10 days, means for one complete cycle it requires only 10 days instead of 30 days which is required in a conventional sludge drying bed process for different types of sludge, because this is already digested sludge, so it will require very less time for dewatering, drying. So this is normally 10 days. And then you can see the another data which is given is, that is 0.3 meter, that is the thickness of the sludge layer that should be applied in the maximum thickness up to 0.3 meter. So for this data how we can do the calculation? So here if we see, that is first of all again we have to, depending upon the volume of the sludge that will be generated in a one cycle. So here if we see that is the amount of the sludge that is generated per day. So if we presume a complete cycle takes 10 days, so within 10 days how much total amount of the sludge that will be generated, and if we divide with the thickness of the layer, so how much the bed area requirement would be there. So this is like how we can calculate the total bed requirement that is required for sludge drying bed. And now instead of assuming the size of the bed, we can assume the number of the bed also. That is another way of solving the same thing, the designing the sludge drying bed. So here the total plan area for each bed, if we see, that will be total area divided by the number of the bed, and that comes around 254.43. And for this area that is coming, so we have to check whether this area we have got that follows the per capita contribution area. So here if we see per capita wastewater flow, if we assume that is 150 liter per capita per day, so if we presume per capita wastewater flow to be assumed as 150 liter per capita per day, so for the given amount of the wastewater flow that is generated around 50,000 meter cube per day, so this we can convert into liter per day. So this is multiplied by 10 raised to the power 3. So total this much liter per day is generated, and if we divide per capita water generation rate, so that is 150 liter per capita per day, which is generated per capita basis. So we can find out how much population that is being served by this wastewater treatment plant. So here it comes 3,33,333 persons are capita. So now if we divide this total area with this total population, so we can find out that is the per capita area that comes around 0.023 meter square area. So here we can see that the area for this digested type of sludge, that is very less compared to the per capita area requirement for the sludge drying bed for different other types of undigested or mixed type of sludge. So this is how we can do the design of the sludge drying bed. So here you can follow these references, like we have taken most of the material from these references. So thank you.